So in this session on signals and systems, we are going to study one application of correlation, and that is called as ultrasonic ranging. So let us start. Now this is basically used to measure the distance of an object from the transmitter. So what is the technique? What do? We transmit an ultrasonic signal through a transducer. So what we do is we generate a periodic signal electronically and then connect it to a transducer, which could be a piezoelectric crystal. It will convert it into a pressure wave, and that is transmitted through the air. And then the electronics, it listens for the echo. So this will occur because of the reflection from the object. So you got a transmitter, you transmit the ultrasonic wave, it hits the object, gets reflected, and the receiver picks it up. So that is the basic technique. Then what do? Then you calculate the delay between the transmitted pulse and the received pulse, and we shall see how we are going to do that. And once this delay is known, then you can calculate the distance by using the speed of sound. So that will be V into delay time divided by 2, because understand that the transmitted signal is going to the object and then coming back. So it is actually traversing the distance, which is 2 times. So therefore distance will be speed of sound multiplied by delay time divided by 2. And as we know, the speed of sound in air is 343 meters per second. Okay. And the one application of this is in robotics, where a moving vehicle may detect an object and take evasive action. All right. So in MATLAB simulation, what are we going to do? So we said that we are generating an ultrasonic signal, which means it is above the audio range, about 20 kilohertz. So in this particular simulation, I am choosing a frequency of 50 kilohertz, certainly about 20 kilohertz, and 5 cycles are generated. Now 5 cycles we are using just to keep the thing simple, so that waveforms would be easily seen. Then as soon as the 5 cycles are over, the receiver starts functioning after the transmission is complete. So to avoid interaction between transmitted and received signal, that is what we do. So we start the transmission of the sine wave, and after 5 cycles the transmission stops. As soon as it stops, then the receiver is put on and listens for the echo. Now the received signal is represented by the delayed sine wave. Now random noise is generated as soon as the receiver is put on, and this is added to the received signal. So what I am describing is what we are going to do in our simulation. So we first generate a sine wave of a definite time duration. Then we generate a noise signal which starts immediately after the transmission of the entire signal is complete, and then this noise signal remains for the entire duration of our time window. Then we will generate a delayed sine wave to simulate the reflected signal, and that is added to the random noise, and final correlation is calculated and its maxima is located, which gives the delay. We'll explain this further, but for the time being, just note that we generate a signal which is the addition of the reflected signal plus the noise, and then find the correlation of the transmitted signal with this, and delay the transmitted signal as we find the correlation, and the point of maximum correlation will tell us what is the delay. This will be better understood as we go on. All right. So this graphical picture will make the process clearer. We generate a sine wave here, and this is lasting for 100 microseconds. Note that on the x-axis we have plotted time in microseconds, and on the y-axis is our instantaneous amplitude. So we are generating a sine wave with 5 cycles in order to represent the transmitted signal. Once this is over, then it waits for the remaining time window, which goes up to 600 microseconds. In an actual system, this could be much more, But right now I have used only 600 microseconds so that we are clearly able to see the sine wave that we are transmitting. The nature of the waveform is clear when I choose this small. If I make this very large, you may not be able to see the nature at all. All right. So how do we generate this transmitted signal? We first generate these 5 cycles, and for the remainder of the time we simply generate zeros and put them in sequence. Then we simulate the received signal in this fashion. We provide a delay from 0 up to some value d, which in this particular case happens to be 200 microseconds, but in our program we can change this. So in order to generate this signal, to simulate this signal, what we do, we generate a number of zeros right from the time 0 up to 200 microseconds. Then we replicate this sine wave. Of course, in general, the received signal will have a smaller amplitude because of the attenuation. But we are assuming here that we have put an amplifier so that this amplitude is same as this amplitude. And again, 5 cycles of this are complete. And for the remainder of the time, we put zeros. Then what we do, then we generate a random signal to represent noise. But understand that we are putting the receiver on only after the transmission of the pulse is over. After that, we put the receiver on. Otherwise, the received signal will interact with the transmitted signal. So therefore, what we do is up to 100 microseconds, we put zeros. And after that we generate our noise. And what we have shown here is actually the addition of this received signal plus noise. Now see the significance of the presence of noise. You can hardly note which is the starting point of the received signal. See, if you had an ideal system whereas there is no noise at all, then these waveforms can be clearly seen on the CRO, and you can easily mark off this time, that is 200 microseconds, that is the delay, and you don't have to do anything else. However, in practice, the signal is always corrupted by noise, and as you can see here, you can hardly see the start of the sine wave. And this is what we want to detect in spite of the presence of the noise. That is why what we do is, we take the correlation of this transmitted signal with the received signal, which is yt plus noise, and then delay this. As we keep on delaying this, when the delay becomes equal to 200 microseconds, this will exactly overlap with this signal and correlation with the received signal will be maximum. Note that as far as the correlation of the transmitted sine wave with the noise is concerned, that is going to be very small, because the random noise changes in a haphazard fashion. There is no similarity between noise and the sine wave. So when you calculate the correlation between the sine wave and the noise, that part is zero. So this correlation most of the time will have a value corresponding to the correlation of the transmitted signal and the clean received signal. And it will become maximum, which corresponds to the delay equal to 200 microseconds, because that is the time when this exactly overlaps the received signal. So this tells us that the delay is 200 microseconds, and then we can calculate our distance. So basically, we have to write a program to generate all these signals and show that correlation is maximum, occurs at a delay which is equal to the delay suffered by the received signal. Okay. So delay is displayed on the console, which in this case, when I ran the program, turned out to be 199 microseconds. Actually, every time you run the program, there could be a slight error which can be different because the noise is quite random. So it could be 199 microseconds, or it could be 200 exactly also, or maybe a little more and a little less. So within certain error, you will get your delay. Okay. So as I said, the error could be more or less since the noise is random. Okay. Now this is tested for one value of delay. So in our program, we can change this delay and again test it. So we change the delay to now 300 microseconds. And now you can see that the peak is occurring at a delay of 300 microseconds, which will give us the delay value. So delay displayed on console in this particular case happen to be equal to 300 microseconds as well. So in that case, you can calculate the distance, that is velocity into delay by 2. So 343 meters per second is the speed of the sound in air. This is multiplied by 300, that is the delay, multiplied by 10 raised to minus 6, because this is in microseconds, divided by 2, that is so many meters, or in terms of centimeters, you can calculate this as 5.145 centimeter. All right. So we have got an overview of what the program is going to do. Let us look at some more details. So let's look at the timings in simulation. So this entire time window we have divided into so many sections. So you have one section from 0 to T1, another from T1 to T2, another from T2 to T3, and finally from T3 to the end of the time window. So what we need to do, between 0 and T1, we need to generate the sine wave. Then between 0 and 200, in order to generate this waveform, between 0 and the delay, we need to generate all zeros. Then you generate this sine wave, again all zeros. For transmitted signal also, beyond 100 microseconds, this has to be all zero. Now here the noise is generated from 100 microseconds, because 100 microsecond is the time at which the transmitted signal ends. So the receiver starts looking at the input, and that is where the noise is generated. So what you are seeing here is actually the addition of this received signal plus the noise, and finally the correlation. All right. So what are the values? So we have chosen t equal to 20 microseconds. That is the time period of this sine wave, which corresponds to 50 kilohertz frequency. And since we are transmitting 5 cycles, this t1 clearly will be equal to 5 times t, that is 100 microseconds. Okay. Then t2 is the delay t. So right from 0 to, in this particular case, t2 is going to be 200 microseconds. T3 will be equal to this delay d plus 5 times t, because received signal also has 5 cycles. So this is d plus 5t. Then T4 is 30t. Remember, we have chosen a time window up to 600 microseconds. So time period is 20 microseconds. So 30 into 20, that will give you 600. That is your T4. So once you have these boundaries known for the time, you can generate the intermediate, all the values by using time vectors. So you can generate a time vector T1 from 0 to T1, then T2, which will go from T1 to T2. So you have to add, because it is the next sample after T1. So you said T1 plus TS to T2. Then T3, third vector, T2 plus TS to T3. And finally the fourth vector, T3 plus TS to T4. Okay. And we'll be using all these terms in our program, so that we'll be able to generate all these various waveforms and then show that the correlation occurs at the delay time. Maximum correlation occurs at the delay time. Okay. But before we look at the program, we need to correct for continuous time. Understand that the XCOR function that we are going to use, basically it calculates the discrete correlation. So the value of Z that you will get, you have to multiply it by TS in order to get the correct value for the continuous time simulation. Similarly, I also will have to be multiplied by TS in order to get the correct time. So Z is a sum. To convert it to an integral, we should multiply by TS. But in this application, the actual value of Z is not important. Remember, what we are trying to do is simply the value of the delay at which the correlation is maximum. The exact value of the correlation is unimportant. So even if we do not scale Z in this particular program, we need not worry. But the delay we must scale. So we need to find the delay at which Z is maximum. Now delay is returned as a number of samples. Therefore, this needs to be multiplied by Ts to convert it to time. That is what you need to do. Okay. Now finding the delay at which the correlation is maximum. So let us see how do we do that. So first of all, we execute this statement. So it will give us all values of correlation for all values of delay. And now what you do, you execute this particular statement. Now look at the first, this wavy sign. This symbol is used to ignore the results for Z. So we are not interested in the values for Z, but we are interested in finding out what is the index for I at which Z is maximum. So this function actually returns Dmax. So Dmax is the index for the delay at which the correlation is maximum. And as we said, the symbol, this particular symbol is used to ignore the result for Z. We use this to get the delay. So how do we do that? Dm is I, Dmax. Understand? Dmax is the index. So we need to find the delay by using this index for the variable I. So I Dmax multiplied by Ts to convert it to continuous time, and multiply by 10 raised to 6 in order to convert it into microseconds. That will be your Dm. Alright. With this background, we are now ready to study the program. So this is as usual clear CLF, CLC. Now F equal to 50,000. We said 50 kilohertz is the frequency. So we choose the sampling frequency. Remember, for continuous time simulations, the sampling frequency has to be much larger. So in this particular case, we have set F into 100. So the sampling time, which is the reciprocal of the sampling frequency, is given by 1 by Fs. So T, which is the time period of the sine wave, is clearly reciprocal of this frequency, 1 by F. And now we specify the delay. So if we change this statement, our delay will change and we'll get a different result. But right now here, we are choosing 200 microseconds as the delay. And since our calculations are done in terms of seconds, we first convert it into seconds by multiplying by 10 raised to minus 6. Okay. Now we generate our time vectors that we have already discussed. So 0 to 5t, that is up to t1. Then t2 is 5t plus ts. Mind you, from here you must take the next sample. Then ts is your sampling time, and d, that is the delay. That is the end of t2. Then t3 is starting from d, you add ts. Ts is the sampling time again. And then from d plus ts, you go by 5 times t. Because remember, the received signal also has 5 cycles. And finally, T4, that is D plus 5T plus TS plus TS. So it becomes 2TS. Then you have sampling time and 30 times T. As we said, our window is 600 microseconds. T is 20 microseconds. So this is 600 microseconds. Then you calculate the length of all these arrays. So length of T1, length of T2. The reason for calculating the length, which gives you number of samples in each array, in each time array, is because then you can appropriately put zeros wherever they are required. Remember, for the transmitted pulse, first 5 cycles you generate and then you have to put zeros. Then for the received signal, for the first 200 microseconds it's 0. Then you have to generate 5 cycles. After that again you have to put zeros. That is why, and so on. So that is why you find out the number of samples in each time array. Then you generate x1, so sine of 2 pi ft, f into t1. Then x2 zeros, so rest of them are 0. So 1, 2, n2 plus n3 plus n4, all these times it is 0. And then you put them in sequence, concatenate them. So x equal to x1 followed by x2. So this is my sine wave and these are all zeros. Okay. Next, I generate the entire time vector, that is sequence of T1, T2, T3 and T4. Now we want to generate the received signal. So first you have got zeros from 1 to N1 plus N2. Then you generate your sine wave, and again you generate zeros and you concatenate all of them in order to get the received signal. Next, you want to generate the signal which is a combination of the received signal and the noise. So what you do, first your noise is from zeros from 1 to N1. So that I call as NY1. Then NY2 is the random signal. This is where your receiver kicks in. This is where the receiver starts. So that is minus plus 10 star random 1 and 2. And in the third segment, you add the received signal to the noise. So this is what you get. That is your NY3. And in the fourth segment, after the received signal sine wave is over, then you need again a random signal, noise signal. So that is generated. So you now put all them in sequence, NY1, NY2, NY3 and NY4. Put all of them in sequence and you get your NY. Then, as we have already discussed, you calculate your calculate your correlation by using the XCOR function. Then find out the D max, that is the index for the delay at which the correlation is maximum. So you multiply by TS and multiply by 10 raised to 6 so that you get this in microseconds. Then these couple of statements are used for displaying this delay. Okay. Then you plot all the waveform. So that is straightforward. Again, we have discussed all the plotting statements before, and you can understand them. So all the rest of the statements are for plotting. You can just go through them, and I'm sure you will be able to understand what we are doing. So once we have entered this program and we execute it, we get all our waveforms here. So this is the transmitted signal, this is the received signal, this is the received signal with noise, and this is the correlation, which clearly tells you that at 200 microseconds, the correlation is maximum, and therefore delay is equal to 200 microseconds, from which you can calculate the distance. All right. So in this particular session, we have discussed one application of correlation, which is for distance measurement using ultrasonic waves, and these are often used in robotics. And that's all in this session.